everybody. We're going to talk about section 2. And oh, let's welcome another friend who just decided that he'd literally climb up. Oh, say hi, Freddie. He's not a big talker. We're going to talk about computing limits in this fun-filled section of chapter 2. And you might be wondering, computing limits, isn't that what we did in the last section where we would actually come up with an answer? That was more from a graphical point of view. We would look at pictures and determine where that guy is going, where that guy is going. Do they meet up the same spot? Do they split off? Does not exist? Is it a number? Is it an infinity? We're going to talk about more of how to do limits from an algebraic point of view. We're going to talk about what we can do just instead of having to graph everything. The reason why we had to graph so much in the last section is we had a lot of denominators that gave us those points of discontinuity that allowed things to explode just like it did right there. And we learned a thing or two. And what we learned a thing or two is going to actually come into play right here. According to what I had typed down, A is going to be a real number, K is going to be a real number. And in this case, if I were to take the limit of a number, I'm getting a number. Then what that means is if I were to graph the equation y equals 4, what I'm going to get is a perfectly horizontal line of 4. And so the limit of who cares of a horizontal line of going through 4 is always going to be 4. So that makes life pretty easy. If I were to take the limit as x approaches 3 of x, that equation is y equals x. That's a perfect diagonal line. All I have to do is just plug in x. So this probably being the most important one, what this says is if I don't have to worry about things exploding, if I don't have to worry, and this is an A and B, if I just have a regular line, all right? So I'm going to throw just a regular curve. Right? No crazy points of discontinuity, no asymptotes, no explosions. All I have to do is if I plug in a point, just plug it in. That's nice. However, and that's if it is x. That's if it is x. If I have 1 over x, which is this equation over there, and by the way, 1 over x also has to do with like 3 over x or 4 over x. As long as it's over x and on top you have a constant, as I approach 0 from the left, I go down to negative infinity. And as I approach 0 from the right, I go to positive infinity. These are just shortcuts that we can remember should we choose to do so. Okay. Can I get rid of that? Hey, I can get rid of that. Look at that, buddy. Look at that. He's hitting me in the back of my head with his tail. I love cats. I love them. In fact, I'm wearing a t-shirt with a cat on it. All right. This is some fun theorems that you're just going to not necessarily memorize, but we'll break down and I'll explain what everything means. If we're taking the limit of a polynomial. So if I take the limit of, I'm just literally writing this out and making this up, x squared plus x plus 3. What this first guy is saying is I take the limit of each part individually. So as we do problems, and we're going to spend this lesson just really breaking down these problems and using these theorems, and it'll seem like a gratuitous waste of time when we do some of it, but that's part of my math teacher job, is to make sure that we show all of our steps. We're just taking the limit of every one. So what this is saying, according to the previous theorems, is I would just do the limit of x squared plus the limit of x plus the limit of 3. And according to what we wrote down, I could just say 3 squared plus 3 plus 3. And that's what A is saying. What B is saying is if for any reason I were to make this 4x squared, I can just kind of deal with the 4 and the x squared individually. If f of x represented 4 and if g of x represented x squared, I could just take care of these individually, or in other words, just still plug in 3. What this is saying is if I have something that doesn't explode. And what this says here is provided that L, the limit, of course, these just mean limits. My limit answer is not 0 on the denominator, the bottom. This is basically saying plug them in. So if you have x over 5, I could still just plug things in. And since 5 would make the bottom explode, I could still plug in 3. So all of these things are basically saying you can plug in 3. Plug in 3 to every single x. These rules let you do that. So breathe that in for a second. That's what these 3 theorems are saying. Furthermore, I could look at these theorems, and again, I can just simply plug in A. Now, this is saying if you have a cubed root, square root, whatever, you're allowed to move the limit inside. So it might be beneficial at times for you to do that. Now, right now, it doesn't seem so obvious. And when we do some practice problems, we'll probably do that. But, this is saying that we're allowed to do that. And E was basically saying, I already mentioned E before. If I have something like the limit of the limit as x approaches 5 of 3x to the x squared by, I'm allowed to just rip out the 3 and do the limit as x approaches 5 of x squared. There are times where that, again, seems like a gratuitous waste of time. Like, why do we have to show that work? We really don't. But it's just these theorems are here saying I'm allowed to do that if I want to. And at the end of the day, I'm just going to still plug in 5 and multiply the whole thing by 3. It's just these rules exist, telling me I am allowed to do that in the moments that it seems convenient to do so. Whether we do that today or not, we'll find out. Okay. Rule number 1. And again, there's no specific order in which this has to be done. I'm just, being a math teacher, and that's my job. I'm a math teacher. I teach middle school kids. I'm just going like ridiculous and showing all of my work. According to all the rules that we have, everything that we were given, I'm allowed to say, like, oh, look, we have something divided by something. So let's say the limit as x approaches negative. Oh, let me write that out better. That looks awful. The limit as x approaches negative 1 of x cubed plus 2x minus 3 over the limit as x approaches negative 1 of 4x minus 2. That's what one of the theorems, the theorem that said the limit of f of x over g of x is the limit of f of x over the limit of g of x. That's the one theorem. Similarly, I can now, according to another one of the theorems, if I have several terms being added together, I can now go one step further and say, well, technically we need to take the limits of all of these. So the limit as x approaches negative 1 of x cubed plus the limit as x approaches negative 1 of 2x minus the limit as x approaches negative 1 of 3 all over the limit as x approaches negative 1 of 4x minus the limit as x. Remember when I said gratuitous, waste of time, or whatever I said? That's what we're talking about here. If I even want to go one step further, I can do this. If I even have space for it, I might have to write a little bit smaller, but I'll do it. I'll do it because, I'm sure you're dying to see what I could do to make this even more crazier. That would stay the same. What I would do is I would pull a 2 out. That was one of the theorems. I think it was the fourth one. Again, not completely necessary, especially after you find out in the next slide what we could just do. The limit as x approaches negative 1 of 3 all over. I could do exactly the same thing here for the limit as x approaches negative 1 of x minus the limit as x approaches negative 1 of 2. Now what we can do is we can take each individual piece and solve. So this guy becomes negative 1 cubed. This guy becomes plus 2 times negative 1. This guy becomes minus 3. Remember the limit, and that was the first thing that we saw. If you just take the limit of a constant, you have that constant. And this was the second thing we saw. If you take the limit of x, you just plug in negative 1. Four times, oh, look, it's the same thing again, negative 4. Minus 2, because there's nothing to plug in 1 for, or plug in negative 1 for. And, oh boy, am I out of space. So I'll just do it all in one step. Negative 1 cubed is negative 1. Minus 2 minus 3 is negative 6. Negative 2 minus 2, or negative 4 minus 2 is also negative 6. And this whole thing becomes 1. So at the end of the day, really, all I did was plug in negative 1 to every single x. And I was allowed to do that because the denominator wouldn't explode. You know, if I plug in negative 1 to the bottom, the denominator didn't explode. However, I wrote all this stuff down just to prove to you that those theorems weren't a complete waste of time. Complete waste of time. Now, a little handy shortcut that we learned from all of those theorems is as long as we have just a polynomial, and by definition, a polynomial could look something like this. 3x squared cubed minus 5x plus 10. What you're not going to see is negative exponents. Okay, a polynomial always has positive exponents, so you don't have to worry about discontinuity. You don't have to worry about those points of discontinuity, that they're explosion points. As long as you have a polynomial like that, and I ask you to take the limit as x approaches, I don't know, some number of that whole thing. What this theorem is telling you is that just plug a into x. Just plug it in. There's not, if you have a polynomial, it's just going to be a curve of some kind. You know, in this case, this is going to be a cubic, so it's going to look like that. You don't have to worry about holes in the graph. You don't have to worry about asymptotes. Whatever your limit is, whatever it approaches, it's going to be there because nothing crazy happens in this polynomial, or any polynomial for that matter. So a lot of the theorems that we wrote down can be bundled up into this. That's pretty convenient. All right, so let's take our knowledge of what we just learned and just do it. I'm not going to go crazy and write all this out like I did with the problem a few problems ago or a few slides ago. I'm just going to plug it in. I'm going to make sure, however, that when I plug it in, I don't get 0 on the bottom. So if I were to plug in 3, 3 minus 2 is 1, we're good, and 3 plus 3 is 6, we're good. So let's just plug it in. 3 times 3 squared minus 3 over 3 minus 2, 3 plus 3. 3 squared is 9 times 3 is 27. 27 minus 3. 3 minus 2 is 1. 3 plus 3 is 6. 24 over 6 is 4. Basic. PEMDAS. Again, the reason why the limit is just a matter of you plugging in 3 is because if I were to graph that, and I'm not going to, but if I were to graph that, if I actually were to look where x is 3, I get a spot on the graph, and the spot is 4. I don't have to worry about, like, where is it headed? Where is it going? No, 3, when x is 3, f of x is 4. Similarly, I'm going to make sure that if I plug in 4, I hit no roadblocks, and I hit no roadblocks. So this is just going to become 4 minus 3 to the 32nd power, 4 minus 2, 1 to the 32nd power times 2, 1 times itself a whole bunch of times, just 1. And 1 times 2 is 2. Simple. Here's the thing. There will be times where I ask you for a limit. And usually what we did in these cases, we graphed these, or we made a chart or something like that. If I were to plug in 2, unlike the previous problems, if I were to plug in 2, things do blow up. But I'm looking at this problem and I'm having flashbacks of Algebra 2 here. If I have a rational function, which means a numerator and denominator, if both the numerator and denominator equal 0, which I have, look for a common factor to eliminate. So that's what I'm going to do. If I were to plug in 2, I'd get 0 over 0. But what I'm going to do instead is I'm going to factor. Now, you might remember difference of squares. And if you don't, here's what it looks like. Difference of squares is if you have a square minus a square, x squared minus 4, 2 squared. You can write that out as x plus 2, x minus 2, which is what I did. On the bottom, I'm just going to wrap it in parentheses so it looks better. I have that. If I'm multiplying things, doing nothing but multiplying inside my fraction, inside my rational, if I have something up here that's literally the exact same as down there, I can just get rid of it. It's gone. Okay, you're allowed to simplify fractions if you're just multiplying. So that leaves me with the limit as x approaches 2 of x plus 2. That's a polynomial. And according to the polynomial rule that we just had not too long ago, all I have to do is just plug in 2 and I'm donezo. Donezo. Dunzo, of course, German for I am finished. I think it's German. Maybe it's Portuguese. I don't know. If I were to plug in -4 here, that would be 16 minus that would fall apart, and that would fall apart, so we'd get a 0 over a 0. Again, that's no good. You can't have 0 over 0. It doesn't make sense. It wouldn't be prudent. So what I'm going to do is I'm going to see if I can factor anything. On the top, I can bring a 3 out of both of these, so I'm going to factor out a 3. On the bottom, I'm thinking of 2 numbers that add up to invisible 1, and this is the reverse FOIL method. 2 numbers that add up to 1 and multiply out to -12. Oh, how about 4 and -3? So if I have 4 and -3, that turns into x plus 4, x minus 3. If you're looking at that and you're like, I don't understand, look up factoring quadratics and you're going to see a cornucopia of stuff that you can watch. Most importantly, something times something over something times something. Those two somethings are the same. Get rid of them. And that leaves me with 3 over x minus 3 as the limit approaches -4. Can I plug in -4 now? Sure can. 3 over -4 minus 3 is going to be 3 over -7. So I'm just going to write out -3 over 7 because that looks a whole lot better. Radicals. I thought that was just a word that the Ninja Turtles would say, right, guys? Well, it's not. Square roots are radicals. Cube roots are radicals. Anything with a root's a radical. And the problem with this problem is you have a fraction and you have a radical. And if I plug in 4, I get 4 minus 4, which is 0, and I get the square root of 4, which is 2 minus 2, which is 0. So that's a problem. So we're going to do something called rationalizing the function. It's basically you take, if you have a binomial, if you have 2 things on the bottom, you multiply the top and the bottom by the same exact thing. You just switch the sign in the middle. Okay, that's how you rationalize the function. X plus root x plus 2, root x plus 2. Let me rewrite this out to make it look a little bit prettier. Okay. That's going to equal the limit as x approaches 4 of. Now, if I'm going to multiply, I'll throw parentheses around that and throw parentheses around that too, and I can extend that fraction bar to go all the way across. Now what I have is this. I have x minus 4 and root x plus 2. I have on the bottom root x minus 2, root x plus 2, and an unnecessarily long fraction bar. No big deal. What do I do now? Well, I have all these markers. I'm going to utilize them. I'm going to FOIL. A binomial times a binomial means I do the first part, the outer part, the inner part, and the last part. So x times root x is x root x. X times 2, 2x. Minus 4 times root x, minus 4 root x. Negative 4 times 2, minus 8. On the bottom, root x times root x is going to be root x squared. Just x. Just x. I'm going to have root x, Lady Gaga. I'm going to have root x times 2, so plus 2 root x. And I'm going to keep this color out. Watch. Minus 2 root x. It disappeared. It's almost as if I knew that was going to happen. I did. Negative 2 times positive 2 is minus 4. So let's write that all out in one big color. Green, which is my favorite. I have the limit as x approaches 4 of x root x plus 2x minus 4 root x minus 8 x minus 4. Now, here's the issue, and I'm just going to tell you what's going to happen ahead of time. If I plug in 4, I'm still going to get 0 over 0. So in the previous problems, I said something to the effect that if you can, factor and see if things go away. Now, you might be looking at that top guy right there and saying, I'm not factoring that. There's nothing in common with those. Wrong, wrong, wrongity, wrong, 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 wrongity, wrong. Remember factor by grouping? No one liked it. But I'm going to rewrite that as 2 groups. I just turned that plus sign into a minus and moved that negative inside. I'm going to take turns factoring each parentheses here. What can I bring out of that parentheses? I can bring out an x. An x comes out. So equals limit. I can bring an x. An x is common with both of these guys, so I can bring an x out. When I do that, I'm left with the square root of x over there, and I'm left with plus 2 right there. Plus, what can I bring out of here? A minus 4. So if I bring a minus 4 out, if I bring a negative 4 out of that guy, I'm left with just root x. And if I bring a negative 4 out of that guy, I'm left with 2. No way. No way. Am I done yet? No. But if you remember factor by grouping, and similar to what I mentioned in the previous slide, if you don't remember factor by grouping, watch a video. What I can do now is, since I have a root x plus 2 in common with both of these, I can bring out the root x plus 2. After pulling out a root x plus 2 out of both of these, I'm left with an x and a negative 4. X minus 4. All that's going to be over. Oh, get out of here. Oh, no. No way. Because now I could just do this. And I'm left with the limit as x approaches 4 of root x plus 2. Well, let's plug it in, baby. Root 4 plus 2 is 2 plus 2. Whew. Oh my gosh. I never realized this was so much fun, says you. All right, I decided to have a wardrobe change. But let's take a look at what we have here. We just did a problem where when we plugged in our number for the limit, we got 0 over 0, and that was bad. And we decided, all right, well, if we get 0 over 0, maybe there's some kind of factoring that I can do and make things go away. And then once I make things go away, it won't be 0 over 0 anymore. Well, that's all fair and good, but this kind of leads us to the what if I can't factor, or what if I don't get 0 over 0? What if I get 0 over 5 or 5 over 0? What happens then? Well, if I give you a rational, a fraction, and upstairs I have a polynomial or whatever I have, and downstairs I have something, what this rule is saying right here, and let me break it down to simpler terms, is as long as my limit approaches a number, and as long as I plug in that number and that number doesn't make the denominator 0, I'm just going to plug it in. So if I have something like this, like I don't care about the top. Let me say this. I'm just going to come up with a very quick, very basic, very easy example. The limit as, that's supposed to say limit, x approaches 3 of x minus 3 x plus 5. Oh my goodness. Got a lot of lag on this guy today. A lot of lag. Much better. So say I have something like that, and a lot of people might be apprehensive about this problem because you're going to be like, well, if I plug in 3, I'm going to get 0. Yeah, you sure do in the numerator, but in the denominator, you get 8. And last time I checked, 0 over 8 is a number, and that number is 0. You're allowed to get that. That's fine. The problem happens when you get 0 over 0. So 0 over 8 is okay. What B is saying is if I do get 0 on the bottom, okay, if the denominator, if after I plug in 3 or whatever, or if I change it to this, let me take the limit as, that's supposed to say limit again, limit as x approaches negative 5 of x minus 3 over x plus 5. You're going to look at that and you're going to say, oh, that's no good, because if I plug in negative 5, I get 0 on the bottom. I'll get negative 8 on top in the numerator. I'll get 0 on the bottom. That can't be. Well, this is the Mean Girls Lindsay Lohan method of understanding limits. What this guy is saying right here is if I do plug in negative 5, which is A, and the bottom is not 0, I'm sorry, if the top is not 0, okay, but the bottom is, I'm not going to just be like, oh, I have to come up with some kind of factoring or something like that. No, if you have a number over 0, that's when we say the limit does not exist. Okay, so to break it down really quickly, what we learned over the last several slides is if you get 0 over 0, you're going to have to do some type of factoring. You're going to have to do some type of factoring to get rid of like a factor, make it go away, then try plugging things in and see what happens then. If you get 0 over a number, your answer is 0. If you get a number over 0, your limit does not exist. So breathe that in, take a minute and try to remember that, because it's very easy to forget. It's very easy to see that 0 on the bottom and automatically freak out, but the only issue is when 0 is on top. Rules. Let's see what we have here. Just if I plug things in, and let me do the mental math to the left side, and to the right side I'll figure out what I have to do. Actually, no, I'm just going to do it on the right side. I don't know why I said that. If I plug in 3, I would get 3 squared minus 3 minus 6 over 3 minus 3. 3 squared is 9. 9 minus 3 is 6. 6 minus 6 is 0. 3 minus 3 is 0. This ain't good. So what you saw in the previous slide is now I have to do some type of factoring. So this top is factorable. When you have a quadratic trinomial, what you're usually looking for is what two numbers do I add together will give me negative invisible 1? And those two very numbers, if I multiply them together, what would give me negative 6? So those two numbers would be x minus 3 and x plus 2. Negative 3 plus 2 is negative invisible 1, and negative 3 times 2 is negative 6. On the bottom, I have the denominator, I have x minus 3. Oh, look at that. Boop. And of course, we all knew that that was going to happen. That leaves me with the limit as x approaches 3 of x plus 2. So I can plug in 3, and 3 plus 2 is 5. So when I graph that, what you're going to see is you're going to see a hole at 3, but business is going to be usual at 5. Okay? And not business as usual. You're going to have a hole at 3, but the hole exists when f of x or y is equal to 5. That's how I should have worded that. Let's do again. 3 times negative 2 plus 1. 2 times negative 2 squared plus negative 2 minus 12 is going to give us negative 6 plus 1 is negative 5. Negative 2 squared is 4. Okay. 4 times 2 is 8. 8 minus 2 is 6. And 6 minus 12 is negative 6. So this is just a regular number. It's 5 over 6. That's nice. Just double checking my work, making sure I did everything right. And of course I did. Let's do one last one. One last one. When x is negative 1, I would have negative 1 squared minus 4 times negative 1 plus 1 over negative 1 squared minus 1. On the top, I get negative 1 squared, which is 1. 1 minus, or rather plus 4 is 5, plus 1 is 6. And negative 1 in parentheses squared is 1. 1 minus 1 is 0. So do I freak out and say, oh, I did something wrong? No, the limit does not exist. What's that, Lindsay Lohan? The limit does not exist. Mean Girls. All right. So that should wrap up section 2. More of the algebraic form of what we learned in the last section. The last section was mostly graphic. Graphic, like my favorite novels. All right, that's it.